Today's topic is functions in general, and we will also review something about logarithms. The first thing that we have to talk about is the definition of a one-to-one function. We know that a function is when each input is associated with exactly one output. When each member of the domain is paired with exactly one member of the range, we call a relation a function. But then even further, if each output value of the function is associated with exactly one input, then the function is considered to be one-to-one. So a function is one-to-one if f of a is not equal to f of b, wherever a is not equal to b. So in other words, each x, what that is saying is that each x is paired with exactly one y. Each x, we'll call x the member of the domain, and the y the member of the range. Each x paired with exactly one y, and each y paired with exactly one x. So the big thing is here is the and. Both of these have to be true in order for a function to be one-to-one. So we can do the horizontal line test to check for a one-to-one function. Because if each x is paired with exactly one y, remember we do the vertical line test to tell whether a relation is a function. But if each x is paired with, each y, is paired with one x, then the function will pass what's called the horizontal line test. So if we look at this first graph, you'll notice I'm doing the horizontal line test. And when I do the horizontal line test, I go through more than one point. So that means there is a y, 1, 2, 3, 4, 5, like 5. 5 is paired with more than one x. So this graph here is not one-to-one. But if I go over here at this second graph, and if I do the vertical line test, I see it is a function. But if I do the horizontal line test, every time I draw a horizontal line, I only go through one point. That tells me that this graph is one-to-one. So there are some basic familiar functions that we can look at, and we can decide whether they're one-to-one or not. For example, y is equal to the absolute value of x. The absolute value of x looks like this. We remember it's that V shape. And so what do you think? Do you think that this function is a one-to-one function? Do your horizontal line test. Let's see. If I draw a horizontal line here, do I go through more than one point? The answer is yes. So therefore, this is not one-to-one. Y is equal to the absolute value of x is not one-to-one. And what about the next one? What about y is equal to the square root of x? We remember the square root of x starts at the origin and curves up and to the right, like this. So if I do my horizontal, remember it's curving up. It keeps going up like this. So if I draw a horizontal line anywhere, do I only go through one point? The answer is yes. So we'll say that this one is one-to-one. Okay, so that's what a one-to-one function is. Now let's talk about inverse functions. I know that f of x is equal to x cubed and f of x is equal to x to the 1/3 are inverses. And I know that because when the definition of an inverse is what I get when I switch the domain and the range. So if I switch the domain and the range, the domain, we'll call it for now, for our purposes, the x, and the range for our purposes, the y. So if I switch the x and the y, remember those are the steps for finding inverse functions. Switch the x and the y and then solve for y. So if I switch the x, if I take y is equal to x cubed, and I switch the x to the y and make it x is equal to y cubed, x is equal to y cubed, and I solve for y, I'd have to take the cube root of both sides. So I get y is equal to the cube root of x, which is also known as x to the 1/3. So I know that these two functions are inverse functions. Notice the notation. We've got a function called f, and we've got a function called f inverse of x. We should recognize that notation. So what do we know it's special about inverse functions? we know that they're a couple of things. We know that their compositions are the identity function. So let's talk about what that means, identity function. Let's talk about what that is. The identity function is y equals x. So if I do the composition f of g of x, or remember f of g of x or f of g of x, that's the same notation, different notation, same thing. Then I get, let's see, f of g of x would be x to the 1/3 cubed, which is x. And g of f of x is x cubed to the 1/3 power, which is also x. So x is y equals x is known as our identity function. And so what's special about two inverse functions is that when you do their compositions, they both end up being the identity function. And so consequently, when we do that, when we look at the graphs of inverses, we can look at the graph of y equals x cubed, and we can look at the graph of y equals x raised to the 1/3 power. And we know that they are reflections over the line y equals x, which is the identity function. And the reason why our line of reflection is y equals x is because when we do our when we do our compositions, we get that identity function. So how do we find the inverse of a function? We just talked about that. We switch our x and our y, and we solve for y. So we can do that for a couple of examples. If f of x is equal to negative 2x plus 4, then that means y is equal to negative 2x plus 4. So I'm going to switch the x and the y and make it x equals negative 2y plus 4. And then I'm going to solve for y. So I'm going to subtract 4 from both sides. And then I'm going to divide both sides by negative 2. So I get y equals negative 1/2 x plus 2. And since my original function was called f, then I can call this inverse of f, the inverse of f is called f inverse. And do you think that this function is 1-to-1? Well, let's see. Negative 2x plus 4. Let's look at our graph. Let's go ahead and clear this. And we're going to look at negative 2x plus 4. Now, I don't even need to look at this. I know, I'm expected to know what that looks like. I knew what that would look like. And let's do our horizontal line test. Do you believe that this function is a 1-to-1 function? And you're probably saying, yes, it is 1-to-1. Okay, we're going to do one more. If f of x is equal to x squared plus 1, then y is equal to x squared plus 1. So that means x is equal to y squared plus 1 would be my inverse. So now I'm going to solve for y. So I'm going to subtract 1 from both sides. And then I'm going to take the square root of both sides. And when I take the square root of both sides, I remember plus or minus the square root of x squared of x minus 1. So let's see. Do you believe that this is 1-to-1? Well, let's see. Oh, we forgot to give it a name. So our original function was called f. So we'll call it f inverse, x squared, x minus 1. So here's our inverse. And do you believe it's 1-to-1? Let's see. X squared plus 1 does like this, doesn't it? So if we do our vertical line test, in our head, we see that this is definitely not 1-to-1. Okay. Good stuff. All right, so now we're going to move on to logarithmic functions. The definition, here's the definition of a base A logarithm function. The base A logarithm function y is equal to log base A of x is the inverse of y is equal to a to the x. A logarithmic function and an exponential function are inverses of each other, always. Where a is bigger than 0, so the base of the logarithm and the base of the exponential function will always be positive, and a will never be 1. Okay, so the domain of a log function, log base a of x, is always from 0 to infinity, and the range is all the reals. So let's talk about why that's true. The Domain is the x of the logarithm. So if y is equal to log base a of x, the x is called, remember, that x is called the argument of the logarithm, and the argument of the logarithm always is positive. So that means that x has to be positive, not 0, not negative. We have a vertical asymptote on the graph of a log function. We've got a vertical asymptote at, let's make a big, thick red. Make a big, thick red. There we go. Big asymptote, a vertical asymptote on the y-axis. And getting black here. There we go. And we've got a graph that does like this. Okay. So let's see. We've also want to bring up, let me remind you that we have y is equal to the ln of x, which is the natural logarithm. We call that the natural logarithm. We use base e logarithms a lot in calculus, so we're going to remind ourselves of that. And we've also got log of x, which is log base 10. The log base 10 is called the common logarithm. We also want to remind ourselves that the ln of e to the x is just x, and that e to the ln of x is also just x. Some identities that we need to remember about log functions. So what do we need to really remember about log functions is that the range is all the reals. There's always a vertical asymptote, and the vertical asymptote is going to depend on the argument. Because the argument of the logarithm, the x is going to be in the argument, and the argument of the logarithm always has to be positive. So therefore, the domain of my log function will always depend on what the argument looks like. So we can look at some equations to solve. We're going to solve these equations for x. So I see the ln of x is equal to 3t plus 5. So if I do e to the ln of x, and I do the same thing on the other side, I can make both sides e to the something. And I know I can do that because I can do whatever I want to an equation as long as I do it to both sides. That's an age-old rule, isn't it? So I'm going to do e to the something equals e to the something. And the reason why I'm doing that is because I know that e to the ln of x is just x. And I did it. I solved for x. And let's look at the next one. Notice where the x is in the next example, in example B. The x is in the exponent. So what I need here is I need to use a logarithm to solve this equation. And since my base is already e, I'm going to use an ln. So I'm going to say the ln of e to the 2x is equal to the ln of 10. And I know that ln of e to the 2x is just 2x. And I'm almost done. I just have to divide both sides by 2 now. So I get the ln of 10 divided by 2. Now remember, the ln of 10 divided by 2 is not the same thing as the ln of 5. Let's go in our calculator and let's estimate the ln of 10. So I'm going to do the ln of 10 divided by 2 is approximately 1.151. 1.151. So we're going to get in the habit of rounding to 3 decimal places. 1.151. That's good. Either one is good. You most likely won't have a calculator, so ln of 10 over 2 is also good. Okay, so and then lastly, we've got 3 rules for logarithms, properties for logarithms that we must always remember. The product rule, log base a of x times y is the same thing as log base a of x plus log base a of y. So we recall that the product property or the product rule says that if we have a logarithm where the argument is a product, we can split it up into 2 logarithms and add the 2 logarithms together. And similarly, the quotient rule, log base a of x over y. Notice my argument is a quotient here. The quotient rule or the quotient property says that I can split this up into 2 logarithms and subtract them. Log base a of x over y is the same thing as log base a of x minus log base a of y. That should ring a bell. That should be very familiar. And lastly, the power rule. The power property says log base a of x to the y power is the same thing as y times log base a of x. So remember that power rule that says exponents of an argument can be moved in front of the logarithm. That's what we're talking about here. We used that one a lot in Algebra 2, didn't we? So we're going to need to remember these properties for logarithms. We're going to be using them when we solve equations. We're going to be using them when we do some calculus stuff.